In this video, we complete the picture of the electronic structure of atoms by introducing a fourth quantum number, the electron spin quantum number, alongside the Pauli Exclusion Principle to show how we generate electron configurations. This diagram is the orbital energy diagram for multi-electron atoms showing the relative energy levels for the orbitals, subshells, and shells that electrons within atoms can potentially occupy. Each horizontal line represents an orbital, a region of space in which there is a high likelihood of finding an electron when that orbital is occupied. We represent an electron occupying an orbital by an arrow, one for each electron in the atom. The principal quantum number n is displayed at the left of the diagram. The secondary quantum number L is shown at the top of the diagram. And the secondary quantum number is also known as the angular momentum quantum number or the azimuthal quantum number. The magnetic quantum number ml is shown under each of the horizontal lines. Each of these quantum numbers provides information about the orbital occupied by an electron. More specifically, n gives information about the overall energy of electrons in orbitals, L gives information about the shape of electron distribution, and ml gives information about the orientation of the electron distribution. To complete the picture of the electronic structure of atoms, we need to introduce a fourth quantum number, the electron spin quantum number, ms, which describes the spin orientation of electrons within atoms. It can be shown that electrons behave as tiny spinning charges generating their own magnetic fields, such that when electrons are passed through a magnetic field, they are attracted to either the north pole of the magnetic field or to the south pole of the magnetic field, as if they were tiny electrical charges spinning on their own axes. Given that there are only two possible outcomes for the way an electron spins on its axis, the spin characteristics of electrons are quantized with half of the electrons in an atom or group of atoms showing positive spin characteristics and the other half showing negative spin characteristics. The two possible spin orientations are therefore assigned ms values of ms plus a half, known as an alpha electron and denoted with an arrow pointing up, or an ms value of negative a half, known as a beta electron and denoted with an arrow pointing down. So we now know that electrons within atoms have four quantum numbers associated with each of them, and these quantum numbers help us gain an understanding of the structure of electron clouds that ultimately dictate the chemical properties of atoms, including how atoms will chemically bond to other atoms. The first three quantum numbers provide information about the orbital occupied by an electron, and the fourth, ms, provides information about the spin characteristics of the electrons. Now, it turns out that each electron in an atom has a unique set of four quantum numbers. In other words, no two electrons within an atom can have the same four quantum numbers. And this is known as the Pauli Exclusion Principle and was first postulated by the Austrian physicist Wolfgang Pauli in 1925, leading to the Nobel Prize in Physics in 1945. The most significant implication of the Pauli Exclusion Principle is that it restricts the number of electrons in an orbital to two, and furthermore the two electrons must have opposite spin, one spin up and one spin down, or in other words, the spins must be paired. Now the reason for this is that for any given orbital, the values of n, l, and ml are fixed, and since ms, the fourth quantum number, can only take on two values, plus half or minus a half, then we can only place two electrons into any one orbital, and one of them must be spin up and one must be spin down. If we try to put a third electron into an orbital, then we will be breaking the Pauli Exclusion Principle, as two of the three electrons will have the same four quantum numbers. To demonstrate these ideas, let's consider the orbital diagram for helium, which has an atomic number of Z equals 2, which therefore means there are two electrons in the electron cloud, making it the simplest of all of the multi-electron atoms. And it should be pointed out that what we're considering here is the lowest energy arrangement of electrons in helium, not a situation where one or more of the electrons have been excited into higher energy levels. In other words, what we are considering is the ground state electron arrangement. We can put the first of the two electrons of helium in the lowest energy 1s orbital, and we can use this diagram to identify the four quantum numbers associated with this electron, with the four quantum numbers being n equals 1, l equals 0, ml equals 0, and ms equals plus a half. So how do we do that? How do we identify the 4 quantum numbers? Well, first we can see that the electron lies in the n equals 1 shell at the bottom left of the diagram. So the principal quantum number n would be 1. The electron also sits in an s orbital and an s subshell, where the secondary quantum number L, shown at the top, is 0. The designation of an s subshell is indicative of a spherical distribution of the electron around the nucleus, and we know there is only one possible orientation of a sphere, and therefore only one possible value of ml, which is 0, given by the number underneath the horizontal line. The 4th quantum number can be determined by the direction of the arrow, which indicates the spin characteristics are positive, and so ms is equal to plus 1/2. Now we can place the second of the helium electrons in the same orbital with the same spin, but that will mean that the 2 electrons have the same 4 quantum numbers, and that is not allowed by the Pauli Exclusion Principle. But if I place the electron with the spin down character, then both electrons will have a unique set of 4 quantum numbers, with n, l, and ml being the same, but with the ms value being different. Let's go to the next element and consider the orbital diagram for lithium, atomic number Z equals 3, and therefore containing 3 electrons in its electron cloud. And again, we are considering the lowest energy arrangement, or the ground state arrangement, of these 3 electrons around the lithium nucleus. So we have 3 electrons that we need to place into this diagram. I can place 2 of these electrons in the lowest available energy orbital, that being the 1s orbital, which is also the 1s subshell. And we now know that their spins must be paired, 1 up and 1 down. The unique sets of 4 quantum numbers for these 2 electrons are shown here, being the same as we just worked out a moment ago for helium. If we now try to place a 3rd electron in that same orbital, we see that the 1st and 3rd electrons have the same set of 4 quantum numbers, and that is not allowed by the Pauli Exclusion Principle. So what has to happen now is that the 3rd of those electrons has to be placed into the next highest available energy orbital, and that is the 2s orbital, or the 2s subshell. And what we see now is that the electron resides in the n equals 2 shell, so that the principal quantum number is 2, with L equals 0, ml equals 0, and ms equals plus 1/2. So all 3 electrons now have a unique set of quantum numbers, and we are not breaking the Pauli Exclusion Principle. By the time we get to element number 4, beryllium, which has 4 electrons in its electron cloud, the first 3 electrons are placed in the orbital diagram as they were for lithium, with the same sets of unique quantum numbers for each electron. And the 4th electron is placed in the 2s orbital, which has room for 1 more electron, so long as it is spin paired with the other electron by having the arrow pointing down. This gives the ms quantum number for this electron as minus 1/2, which again gives all 4 electrons a unique set of quantum numbers in accordance with the Pauli Exclusion Principle. Finally, if we go to element number 5, boron, which has 5 electrons in its electron cloud, the first 4 electrons are placed in the orbital diagram as they were for beryllium, with the same sets of unique quantum numbers, and the 5th electron is forced into one of the orbitals in the 2p subshell, giving for the first time a secondary quantum number of L equals 1 and ml equals minus 1. And again, resulting in all 5 electrons having unique sets of quantum numbers in accordance with the Pauli Exclusion Principle. Using the exact same approach, we can continue to construct orbital diagrams for elements 6, 7, 8, and so on through the periodic table, although we do need to do it in a special way, following the Aufbau principle and Hund's rule, which are the subject of an upcoming video.